Yeah, it's not enough.
So the Earth's spinning the wrong way. Are we all in? Shall we start? So by the clock on this wall, it's time to start. And it's my great pleasure to open the Open for Business session with Samali Simpson. So he's going to talk about four-dimensional X-ray tomography. And look forward to hearing it. Thank you.
Thank you very much. I'd like to thank the organizers once more for this great opportunity to report on some of my activities in the field of X-ray tomography, also related to medical imaging industry. So 4D here refers to 3 dimensions plus time, and I will here confess up front that most of my examples will actually be 2 space and 1 time dimension. But in principle, the stuff I'm showing should be useful also for 3 plus time. Again, this quick look at this picture of our Finnish Center of Excellence in Inverse Problems Research that operates all around Finland. We have physicists and mathematicians taking part in this network-like center. So let me start by reviewing the traditional tomography a little bit. There, of course, the seminal contribution comes from Cormack and Hounsfield, who developed the CT imaging technology, which is widely used today. Charles Epstein was nice enough to send me this reconstruction, which is one of the original Hounsfield's reconstructions, where you can actually see also this kind of black space between the skull bone and the brain. At the time, people thought that there's an air gap between the brain and the skull. However, autopsies and other anatomical understanding didn't really support this. Later they found out that this is due to beam hardening effects of X-ray photons of different energy. Yes. Also let me mention Johan Radon, who invented the formula of recovering functions from line integrals and published it already in 1917. I think I like to see these 2 stories, these guys who developed the actual device, actually without knowing about Radon's work, and this work that was 50 years before. I think this kind of knowledge of how this all went would encourage applied mathematicians to try to put the ideas to practice a bit more quickly than in 50 years gaps. Anyway, traditional CT looks something like this. I guess this is a 2nd generation geometry where there are some X-ray detectors, an X-ray source, and the whole thing, these are fixed into each other. It rotates around the patient, usually with very small angular steps, like 1 degree or so. So it collects hundreds of images from all around. Then a formula like this is the filtered back projection, or one of its forms, is applied to the data, RF, and a high resolution picture emerges. Now, what I did actually after my PhD, when I moved to industry in 1999, I started working at Instrumentarium Imaging, a Finnish company that produced different medical imaging devices based on X-rays. They made mammography devices, dental X-ray imaging devices like panoramic machines, and also surgical C-arm devices. There was a strong enthusiasm about developing 3D X-ray imaging devices that are based not on collecting so much data, but few directions only. Take a few images, keep the dose low, and use just regular equipment like these mammography or dental devices to collect the data, and then develop more involved mathematics to deal with such very incomplete and sparse data. This was actually a really big project. Actually, there were 3 projects funded by the Finnish Technology Agency, also known as Tekes in Finnish. As you see, there are many people who contributed a lot to this project. Erkki Somersalo and Matti Lassas are in this meeting as well from this group. This list includes engineers, R&D engineers at the company. Actually, I was one of them through two of the first projects. Academic mathematicians, academic physicists, and other people. So it's really a big effort to develop new products. I'd like to mention also what happened with the companies. Instrumentarium, the whole instrumentarium company, that was actually a much bigger thing than only this imaging part, was bought by GE Healthcare in 2003. So then the company changed, the people were the same. After a while, GE decided that because this Finnish small site is the only one in the whole GE that produces dental imaging equipment, they sold it. So me and my team of R&D engineers moved between companies. The people were the same, the problems the same, the company kept changing. I guess this is the story of modern high technology life. Okay, let me describe to you somehow the main end product of these projects. It's related to dental implant planning. As you might know, these days when someone is missing a tooth, which you know can happen to anyone, not only boxers and hockey players. A friend of mine, Pasi, went to the dentist and suddenly the dentist says that, oh, I have to remove this molar. I said, come on, I mean, it's my favorite tooth, don't take it away. But he said, no, there is some whatever condition in the roots, it just has to be taken away. Also, that's what happened. And this is what they do these days. They drill a hole here. This is the cross-section view of the same situation. They drill a hole, attach a titanium screw there. Sorry about this image. I made it black and white to be a bit more bearable. Anyway, there are these kind of screws, and then the actual implant is attached to this screw. So this hole has to be as deep as possible to make the implant sturdy. However, it's not advisable to damage the nerve that goes here inside a tunnel in the bone. So this is the nerve going there. If you're interested, you can try there. The nerve actually comes to the surface there. There is a point, if you push your jawbone, you will find one place where it hurts. That's where the nerve comes out. So damaging this nerve can cause chronic pain, paralysis of half the face, extremely expensive lawsuits. So this has to be avoided. So the hole has to be deep, but not too deep. So how to measure the proper depth? One option could be to use, for example, a panoramic imaging device, actually invented by a Finnish professor, Erkki Paatero, in the 50s. He founded a company called Palomex, which later became Instrumentarium, bought by Instrumentarium and so on. This was the main product of his. The idea here is that the head is here, you bite this thing here, these come to the temples, the X-ray source is here, the whole device rotates around the head. Here is a narrow detector with 64 pixels horizontally and 1024 pixels this way. The pixels are moved electronically in a way that it actually picks out a sharp layer inside the dental arc. So in one picture you can actually see all the teeth. Here you can actually see the nerve channel a little bit. You can see the sinuses. You can see the ends of these temporomandibular joints. This is kind of an overall view of all the dental structures. But it has some geometric distortion inherent. So accurate measurements are not possible based on this kind of an image. And the same goes with just one X-ray intraoral image. There is some distortion always involved and overlapping of tissues. So what we did in the project was to program new movements to the machine so that it will collect limited angle tomographic data. So the idea is to keep the X-ray source rather fixed. It was actually not an easy task because the machine was designed for a whole different use. So the degrees of freedom were kind of limited, but there was some ingenious mechanical engineering and very programming very close to the machine that roughly speaking this happens. The source stays fixed. In the other end, with the narrow detector, we scan the picture to get something like this, because remember the detector is very narrow, so it's not possible to really take this kind of two-dimensional image. It has to be scanned. In this geometry we could do 11 pictures, total angle of view 40 degrees. Those of you who have dealt with limited angle tomography know that this is an extremely ill-posed problem, although it's a linear inverse problem, but it's very ill-posed. And these images are 1 megapixel each. And actually I've learned over the times I've given this talk that this picture, I'm not really happy with this one, so I prepared you a video that shows the scanning movement. Maybe, hopefully this is a bit more. So we always scan with the narrow detector and turn the machine. So this is roughly how the imaging goes. It takes like a minute and a half to collect all of these, so the patient has to not move too much during that time. Okay, so this machine, based on total variation computations, came out to the market in 2007 after something like 6 or 7 years of intensive research and development work. This picture is taken from the company website where they show how it's used. If you want to see some demos, you can go to this page. What I like about this product is that all modern dental clinics already have a digital panoramic device there. Now, this is just a mathematical software update. We bring the new movements to the machine and the total variation reconstruction. So just by a software update, the previously two-dimensional imaging device becomes a tomographic device. So from the business point of view, it's kind of a nice thing. You can just update the software and you can charge more. This is an actual clinical image of a patient. This picture is like a navigation slide showing where this is taken. Here you can see the cross-sectional view. Here is the nerve channel, so then the dentist can make this measurement. And let me note here there is an important difference in philosophy compared to traditional CT imaging. The data here is very limited. We have limited angle, only 11 images instead of hundreds of images from all around like traditional CT. As a result, this reconstruction is not perfect. You see, for example, this fiducial reference metal ball there for calibration. You can see some ringing artifacts. You see the same ball several times. Also here you can see different kinds of artifacts like this. So it's really not perfect, but it doesn't have to be. The philosophy is radiate the patient as little as possible while still making a 3D reconstruction that's good enough for the clinical purpose, as opposed to the traditional thing, take the filtered back projection algorithm, analyze the resolution, take so many images that you for sure get the proper resolution provided by mathematics. There, I think mathematics is dictating the radiation dose to the patient. Here we do the opposite. We radiate as little as possible and let more mathematics do the work. So about the dose, there are several options for dentists to get this three-dimensional information needed for implant planning. In principle, they could take a head CT, although I don't think this is ethically approvable anywhere, but this is the radiation dose of a head CT. There are dedicated dental cone beam tomographs available. For example, these 3 products. Here are the doses in microsieverts, and you see that this volumetric tomography device gives only 13. So it's like 1 or 2 magnitudes different from the competitors. Yeah, this one.
No, that's yours, but the one that does the full one, the full panoramic, the 2D panoramic view.
Yes. That's the dose.
Oh, that's it.
It's 6. Oh, yeah, it's this machine. It's this machine.
Oh, I see.
The dose is roughly equivalent to 2 panoramic images, and they are like 6 or 7, maybe something like that. Yep. Yes, and a couple of words about how we do the inversion here. We are not using the radon transform and filtered back projection and that kind of operators. I'm thinking actually in quite simple terms about the tomographic problem. Maybe even in these simple terms. Imagine this two-dimensional patient, this time square-shaped, with 9 internal organs, all square-shaped, and the attenuation is given as a number here. So after calibration, we can interpret the numbers coming from the detector. Actually, the photon counts, we take a logarithm and subtract from the maximum. After that, we have something proportional to these numbers, which in this case are kind of length of this path inside times the attenuation. So we get row sum of this small pixel image. Then we turn, we have a column sum, turn again, we get these sums, and as a nod to the great Pythagoras, we have some square roots here indicating the length of the path of the X-ray inside each pixel. So the direct problem of X-ray tomography in the view taken in this research is that, well, we have these pixels and numbers inside. We know some kind of weighted or some kind of linear combinations of these numbers. Knowing the geometry gives us which directions we know. This is the inverse problem. So direct problem, if we know what's inside, then for sure we can easily compute these numbers. But the inverse problem is our X-ray images give us the numbers around, and we should fill in this kind of a Sudoku problem to find the correct numbers. I know this is a very simplistic view, but actually, in effect, the pictures I showed you of the real clinical patient, it's done in this way, although, of course, the number of unknowns, I think, is a few 100 million, and we have some, I think, 42 million data points. So it's just a much bigger Sudoku, but in effect, that's what it is. Of course, there is ill-posedness, and we have to deal with that somehow. So we used a variant of the total variation algorithm. Let me just point out one recent development we did on top of it. So, well, our Sudoku problem can be put in mathematical form in this way. We just look at the geometry to know the lengths of each X-ray inside each pixel. We give a name to the unknown numbers inside, get the vector of unknowns, give a name to the vector of measurements. We get a matrix equation M equals AF plus noise, and then we need to invert. So what we did in the clinical pictures was an adaptation of the total variation approach. There we actually we rounded the absolute value function to make it differentiable and used some iterative minimization. And actually, in addition, there are some steps added by the engineers at the company after I left the company for academia. So actually, I don't really know all the tricks used here, but I know that total variation is in the core of the algorithm. I think our team was the first one to apply TV regularization to real tomographic measured data as opposed to simulated data. And later in this paper we implemented it for this actual case with clinical data. But let me describe you a more recent development in my team. We wanted to get rid of this rounding the absolute value function. Of course, there are many ways to approach the computation of total variation. There is a big bunch of algorithms, but I think very few of them are really attacking the problem in this way, looking at really minimizing the functional. In this case, we are now in 2D, and we are using the anisotropic. This approach needs the anisotropic total variation, where we have the horizontal differences and vertical differences written separately. So the trick here is to go from this formulation, which is defined for non-negative pixel values, to a standard form, standard quadratic optimization problem, which is nice because it's a standard form and standard software has approaches for it. Now we win something in getting to this standard form with inequality and equality constraints, but also we lose something. This is an n-dimensional problem, and this becomes a 5n-dimensional problem. So the trick goes like this. We write the horizontal differences as a difference of two non-negative vectors, the positive part and negative part. Same with the vertical differences. Just a trick like this. And then what happens is that actually if I go back to the previous one, these one norms of the discrete derivatives can be actually written in this nice way. It's just the vector of all ones inner product with the sum of all these non-negative guys. This is kind of the trick there. What we lose is that we have to take this big unknown vector z that has f and then all of these guys here. In 3D we would have two more, obviously. So that's where we lose some, and then these guys are connected. We have inequalities for f and all of these guys, so whole of z has to be non-negative, and then we have equality constraints here. So my student Kati Niinimäki wrote a quadratic programming code for this case. We wanted to try it out with real data. This is the laboratory of Professor Keijo Hämäläinen in my university. Aki Kallonen is his PhD student. Here is a rotating platform. Everything is computer controlled. Here is an X-ray source. Here is a flat panel Hamamatsu detector. We took pictures that look like this. It's a walnut. This is just for comparison. This is the ground truth done from 1200 views. So this is really taken with very small angular steps to get the ground truth to compare with. So this is what's inside the walnut. We chose it because it's kind of like a brain. This is the depth of our medical expertise. And this is just to compare how total variation works with very sparsely collected data. So here, this is filtered back projection, the classical method. Of course, not designed for this kind of a case. It's designed for the case where we have very fine angular sampling. And here we have 23, 15, or only 10 projections picked out from this data set of 1200 projections. And here you see how the total variation brings out these crisp, piecewise constant type reconstructions. And now I've often heard that it's kind of unclear whether someone would like to look at this kind of picture or this kind of picture. I agree. I mean, if someone has, like doctors have really developed an eye for this kind of pictures, maybe these are better. But I'm arguing that at least these are very different results, and I would guess that in some applications what we see here would be more valuable than what one tries to see here. Who knows? But anyway, this is just a demonstration of the power of total variation. It can interpret really difficult data sets in this manner. Okay, so this time-dependent tomography started with the idea that after all these projects I described to you, we realized in my team that, okay, so it is possible to do decent reconstructions from data taken only from few directions. So then, why not try this kind of new X-ray modality where we place X-ray sources at fixed positions in 3D space. Each of them has their own detector, flat panel detector opposite to it. Each of the flat panel detectors capable of doing a good frame rate, for example, 400 pictures a second. So then we could have something here, maybe a patient, maybe a small animal, maybe in non-destructive testing we could have a small mechanical device, something moving here. We image it from several directions simultaneously, which allows us, if we have this kind of sparse angle reconstruction methods, to reconstruct dynamically both in time and space. Oh, come on, now this is wrong video. Ah. Man. Maybe I just... This is weird. Maybe, you know, what I do is where did I put it? Let's see if this helps. It did work before the talk, as it's always the case. Well, anyway, the video I wanted to show is this one. So one of the promising applications, I think, is angiography, where these days people can only view this situation as a projection video. So here there's a contrast agent going to the bloodstream around the heart, and the cardiologist can just view it and deduce something about what's going on in the blood vessels. However, it would be really valuable to see this in 3D. This is one of the applications, potential applications of this multiple view imaging. So let's see if I could fix that. Okay. So to start with, the problem is that X-ray sources tend to cost like 5,000 euros and up. Detectors with such a frame rate tend to cost several tens of thousands of euros. So right at this moment, I don't have a prototype device to really provide me the data I would like to look at. So what we decided to do is to, first of all, start with a 2D situation where we have this kind of thing, several directions at the same time, and simulate data, and actually also collect data from this kind of a situation. By collect real data, I mean to construct in the middle some kind of object that we can modify step by step, and each frame we can rotate an image from different directions while it's not changing, and then go and change it again and rotate again. It would be the same thing, that it just moves and we image it from all of the directions at the same time. So I'll show you an example like that. Before that, let me comment on... So now it's not working again. This one. Okay. So thinking of what kind of computational method to use. So we ended up thinking about the level set method. As you know, the level set method can be used to model mud. So these pieces of mud in Shrek's shower are actually done using the level set method. The inside of the mud is where the level set function is positive, and outside the mud is where the level set function is negative. So in a 2D situation, we have something like this. Here we have the same level set function, this red-orange thing, and now, well, depending on where the level is, we get different sets for the inside and outside of the level. And what's nice about this is that it allows changes in topology in a very continuous, something continuous is happening, the level is rising, still this set here is dividing into several components, and here one component is disappearing, and there is no problem really with this. So actually we are not using the traditional level set method, we use a variant. In the classical level set method, Heaviside function is used. So the idea is that where the level set function is negative, we have 0, and when the level set function becomes positive, then there's a constant. So like the Heaviside function jumps up to 1. What we use in this work is actually this kind of blue function here instead of the Heaviside. So we are modeling the unknown, the X-ray attenuation as G, the blue function, applied to the level set function. So then outside the level set we have 0 attenuation, and inside the level set function itself gives the reconstruction. We can compute it similarly to the classical level set solution. We take a limit when S parameter goes to infinity. Here is our attenuation. Here's the projection and back projection operators, our data, regularization term requiring that phi is smooth. And actually for this one we can prove that there exists a limit in this process, which is actually not available for the original level set method because the Heaviside function is too singular. But for this method we can prove convergence. So this is just to show you the difference between the classical level set method with Heaviside function and with our method, where inside the level set function itself gives the attenuation. So we first tried this out in static 2D tomography, so there is no time dependence here. This is real data from wisdom tooth. Here is for ground truth, this is from full angle measurement. This is just a back projection showing the typical stretching of limited angle tomography algorithms. It's really hard to avoid such stretching. This is our level set method from the limited angle data. I think I'm saying that this is the most efficient algorithm for suppressing these kind of tails or this stretching that I have ever seen. I'm not saying that it's correct around here. That's a tall order because it's really unstable to get something correct here. But anyway, I haven't seen any other algorithm that suppresses these things as effectively, which was really promising. So then we decided to try this method for the time-dependent case as well. So in the two-dimensional static case, the X-ray attenuation is this one, the blue G function applied to a level set function of 2 variables. We take the limit of this function, which satisfies it from this evolution equation, and our Laplace here is just a Laplace operator with x and y. Now with the time dependent, like in Matti's talk, we went to space-time. So our level set function is in 3D, the third variable being time. Then we let this parameter again go to infinity. This is formally the same thing here, although our data also now has data at different time steps. And funnily enough, we have the Laplace operator here looking like this. In relativity studies, it might look weird to have a plus here, but here we just treat time as one of the dimensions. So let me show you what happens here. Our first example is a simulated one. So we just took this kind of an object having a disk with attenuation 1, outside attenuation is 0. So when the time is advancing, one disk is splitting into 2. So we wanted to see what happens with this. Now in the space-time view, this is what we have. this axis is time, so in time the disk is branching out like this. And now I wonder what happened with my... Okay, well these are slices of the reconstruction. Promisingly, we again see some suppression of these things. With Tikhonov regularization, we have all kinds of non-zero stuff around here. With the level set, we nicely get something zero outside here. Here, actually, we don't have a limited angle situation here. It's kind of sparsely sampled full angle situation. So now, again, I guess my video doesn't work. So I'll show it from here again. So this is like the piece of mud in the Shrek movie, but this is our reconstruction in space-time. So when we reconstruct, we just slice this thing at whatever time instance we want. But this was a simulated example, so it's of course easier than actual measured data. So like I said, we wanted to simulate the situation that we would have something changing in time and we would image it from several directions at the same time. Like I said, we don't have that machine, but what we did, we placed sugar cubes on a platform and imaged it. I designed this kind of small animation movie where we have more and more sugar cubes appearing. So you can imagine there's something that changes in time like this, but each time frame we can just fix, let it be, rotate it. In this picture we have taken 120 pictures and did filtered back projection just to show how the object looks like. Let me now show you the level set reconstruction. Here you see for comparison the filtered back projection thing, and here this is computed only from 10 projection. So 10 source detector pairs would give us this kind of a movie. Of course, this is not at all perfect, but also the data is very sparse. And this is kind of a first step to this direction, so I'm kind of I think it looks at least a little bit promising that we could maybe do something with this kind of imaging. Let me show you in this case our level set result, which I believe, again, the video wouldn't play, so let me go here. Oh, and what was the name of it? Sorry about this. So this is a recovered piece of mud in this case, and again the reconstructions I showed you were just slices of this thing at different heights, representing different time instances. And this is really computed from these 10 projection directions only. So this is pretty much all I wanted to say. I'm hoping to build a prototype machine and soon report some dynamic tomographic results for you. Thank you.
When you compared in one slide RBP back projection and total variation, the back
Right.
projection.
It's only back projection, not filtered.
Yeah, but well, is it true that very similar result could be obtained if you just, since all those features are already visible in the back projection,
So you probably can apply some kind of post-processing, maybe using the same total variation,
Yes.
and get very similar results.
Probably so, yes.
Can you tell us then what could be advantage of using total variation?
I think in general, I think it's generally preferable to do something directly from the data and get the result. I think instead of having several different steps that may introduce artifacts. I don't know really. I think it depends on the application, what approach would be best for a given given purpose.
I very much doubt TV denoising would get the image at the bottom from the top, because the top image is those streak artifacts that you always get in.
No, not necessarily.
Unsampled CT.
There are many other, I don't know, there are some clustering-based approaches. I mean, there are so many techniques in image processing.
But if you look at the contrast in the kernel of the walnut, it's very weak, actually. I think it would be really hard to...
No, but you can clearly see all those structures once you can see the.
Well, a fair point.
That's true, but I think there is some value in simplicity, doing something directly from the data, getting the bottom image, instead of getting first the above image and then do some. I think it's probably easier to analyze and understand this kind of one-step thing instead of several steps. But I don't know really. I mean, it depends on the application, I think.
I may make an observation from the chair that actually in material science CT, it's actually usual to not know what the algorithm is, and it spits out a 3D volume rendering, and then it's post-processed to segment and so on. And it's a real problem that they don't know whether their segmentation fits their model or not, because they don't even have a forward model. So, you know, in a way, that's the answer. People are doing that sort of thing and finding it's lacking for that reason. Any more questions? Yeah.
This seems like a setup for some hypermodel with some sparsity constraint. Have you tried that? Because I think it
Right.
actually on time and simplicity is going to probably, you know, be a contender.
Right.
Yeah.
Sure. I'm sure it would be. Yes.
Yeah, I'll show some results in the next talk about that.
Yeah, you know. So.
I think this project was kind of driven by the practical application and the product, and there we saw that the total variation and non-negativity constraint was really useful, and then the continuation project was kind of trying to remove from there the kind of lacking features.
But
Yeah.
the total variation, I mean, that's not exactly the most friendly to work with numerically, and then
Sure, yeah.
in the other in the hypermodel, even that it's at the end of the day all linear algebra. There is you know, LDA when you need it. And then you can project and you can impose pretty easily the non-negativity there, so,
Yeah.
or any other bounds on thresholding. So I think
Yeah, I agree. It would.
I think it would
Yeah.
be worth if you're interested in, you know, fast and simple methods. to do that.
Any more quick questions?
So this is a more general question, because I'm not familiar with total variation. Would you say that the difference between FVP and TV is actually representative? Is like, if I apply in general FVP and TV to the same problem, would I see something like that?
Yeah, sure. I think
Because to me,
yeah.
if I had to pick one of the two, I would pick FVP on that.
Yeah, many people say that. Yeah, I know.
I don't mind to see the noise. The
Yes.
noise is telling you that there is some uncertainty. What I
Yes.
don't like on the bottom part is that the image looks so sharp
Yes.
that you would be tempted to say that there is a feature there, and you jump straight into it.
Right.
Whereas with above, you say, "Oh, wait a minute, I shouldn't jump into it because there is noise."
Yeah, you're really not the only one thinking that way, and that's why I try to be careful here. Just saying that it produces very different images, and if that suits your needs, then it's good to use it. But otherwise, I'm not saying which one is better, but they are different. That I'm saying.
Yeah. No, definitely.
And I think when you have lots of data, I mean, many angles, then it's, I think, pretty much the same image quality-wise what method to use. All the methods will give kind of the correct image, and then it's just what is fastest. And usually, I think filtered back projection must be the fastest. It's so optimized. But in this kind of cases, then it's
And
more
if you start
complicated.
playing with the filtering, with the window, and so
Sure.
on. Would you be able to improve on the?
I'm pretty sure, but I'm really not an expert how to improve filtered back projection. I know some people are really skilled at that, so this is probably an unfair comparison in that sense, because the filtered back projection here is just what MATLAB is giving. It's not really optimized. So
iRadon.
yeah,
Straight from iRadon.
yeah, I think it is. Yes. No, not. Oh,
iFan.
sorry. It's not that, because this is fan beam data. So
iFan. It's
yeah.
iFan, okay. iFan B.
That's the MATLAB.
Right, but it's actually not that. It's the fan beam and back projection have been developed in the company project, so it's a company proprietary code.
Right.
But well, it's the same thing what it's doing, but yeah.
Thank you very much. Yes.